Good morning. Today's lecture is going to be the introduction to sampling distributions. So our learning objectives for this lecture are, by the time we're through, we should be able to explain the sampling distribution of the sample mean x bar, describe the sampling distribution of the sample mean x bar when the population is normal, and find probabilities and percentiles for the same mean when the population is normal. The sampling distribution of the sample mean x bar for a given sample size n consists of the collection of the means of all possible samples of size n from the population. So here's our definition. The collection of the means of all possible samples of a certain size from a population. So we have some facts about sampling distributions. The mean of the sampling distribution of the sample mean x bar is the value of the population mean. So we're going to denote the mean of the sampling distribution of the sample mean x bar as mu sub x, and mu sub x will just be equal to mu, the population mean. Whereas the standard deviation is not quite the standard deviation of the population. The standard deviation of the sampling distribution of the sample mean x bar is going to be the standard deviation of the population divided by the square root of the sample size. And we're going to call this sigma sub x bar, the standard deviation of the sampling distribution of the sample mean, or the standard error of the mean. All right, another fact. For a normal population, the sampling distribution is also normal distribution. So if the population has a normal distribution, then the sampling distribution of the sample mean x bar will also have a normal distribution. And we know from our previous lecture on normal distributions that that's a very nice thing. And even better if we can standardize that normal distribution so we can use the z-score and the z-table. And so it says here that when the sampling distribution of x bar is normal, which we know happens when the distribution of the population is normal, then we can standardize it using this formula, which should look pretty familiar, pretty close to the formula we already used. So you see here x bar, the sample mean. We subtract the mean of the sampling distribution of the sample mean, which is mu sub x bar, and we divide by the standard deviation of the sampling distribution of the sample mean, sigma sub x bar. Or here, we know that mu sub x bar is just the population mean mu, and we know that sigma sub x bar is the population standard deviation sigma divided by the square root of the sample size. Okay, one last nice fact is here, the central limit theorem. The central limit theorem is of huge importance in terms of probability and statistics, but for the purpose of our class, I just want to introduce it to you. You don't necessarily have to have this memorized, but what it tells us is extremely powerful. It says, regardless of the shape of the underlying population, the sampling distribution of x becomes approximately normal as the sample size increases. So we already knew from fact 3 that if we had a normal population, then the sampling distribution of the sample mean would be normal. But the central limit theorem now tells us that regardless of whether or not we have a normal population underlying, if we take a large enough n, then our sampling distribution is going to approach a normal distribution. So that's really, really cool and really, really nice. But we're going to probably focus on the original definition that we had. Okay, so let's do an example. Initial public offerings, which we're going to use the letters IPO. A monitor of IPOs reports that the mean amount of stock offered was $100 million with a standard deviation of $40 million. Suppose that IPO amounts are normally distributed and that we take a sample of 4 IPOs. Find the probability that the sample mean IPO amount will have the following values, and then we have some values here, A, B, C. All right, so we're told here that we have a mean amount of $100 million, and that is our population mean. So we're going to say mu is 100. And we're not going to write 100 million, but we're going to remember that it's in millions. And then we have a standard deviation of 40 million. So that's sigma. The population standard deviation is 40. It says, suppose that IPO amounts are normally distributed and we take a sample of 4. So n is 4. And n equal to 4. 4 is not very large, so we can't invoke the central limit theorem here. But because it said that our IPO amounts were normally distributed, we can go ahead and say that the sampling distribution of the sample mean is going to form a normal distribution of its own right. But in order to talk about that normal distribution, we need to know mu x bar. So the mean of the sampling distribution of the sample mean x bar. The mean of the sampling distribution, we know, is the population mean. Easy peasy. So that's 100. We also need the standard deviation of the sampling distribution. And we know that that's the population standard deviation divided by the square root of the sample size. So for our problem, that's 40 divided by the square root of 4, or 40 over 2, which is 20. So the standard deviation of our sampling distribution is going to be 20. So these are the numbers that we're going to use for the rest of our problem. Mu x bar equal to 100, sigma x bar equal to 20. So let's see if we can answer the question. Find the probability that the sample mean IPO amount will be greater than 125 million. That's our first question, greater than 125 million. So let's draw the picture of our normal curve. Nice bell shape. We know that the mean of our sampling distribution, mu x bar, is 100. And the question has asked us to find the probability that we're going to get 125. So 125 is larger than 100, so we know that should be somewhere out here, 125 million. Okay, so, but it says greater than 125, so that's going to be this area here on the right-hand side. We know that eventually we're going to use our z-table, and our z-table is going to give us left-sided area, so we're going to have to address that eventually, but before we can do that, we need a z-score. So let's talk about a z-score for 125. So we have 125, which is going to take the place of x bar in our formula here. And we have a mu x bar, so we can subtract mu x bar and divide by sigma x bar. So that is, we subtracted the mean of the sampling distribution, we divide by the standard deviation of the sampling distribution, and we find a z-score of 1.25. So the question is, the probability that x bar is greater than 125, and we translated that into the probability that z is greater than 1.25, and we know that that is equal to the probability, that is equal to 1 minus the probability that z is less than 1.25, right? Okay, so now we need to find this probability, and what do? We refer to our table. So let me pull up the table, and I'm looking for z equal to 1.25. Scroll down. Here's 1.2, and I go over 0, 1, 2, 3, 4, 5. So 0.8944 is going to be the number that I need for my problem. Let's go back and plug that in. So this is, according to what we found in the table, 1 minus 0.8944, and that is 0.1056, answers my question. The probability is 0.1056 that the sample mean IPO amount will be greater than 125 million. All right, let's see. Question B is between 120 million and 140 million. So B, between 120 and 140. Again, I can draw my distribution. And I know that mu x bar, right here in the middle, is 100. Question is asking me, between 120 and 140, what is the probability that my sample mean lies there? Both 120 and 140 are higher than our mean of 100, but I'm looking for just the small area in between. And we know from experience that that means we need to take the probability that 120 is less than x bar is less than 140. Well, that should be equal to the probability of x bar less than 140, subtract the probability of x bar less than 120. And we want to translate that into z-scores. So let's find a z-score for 120 and a z-score for 140. I'm going to say z sub 120. And again, we use the same formula. 120, subtract the mean of the sampling distribution, divide by the standard deviation of the sampling distribution. We get 20 over 20 is 1. And z sub 140, 140 minus the mean of the sampling distribution, divide by the standard deviation of the sampling distribution. We have 40 over 20, which is 2. So if I wanted to translate this probability in terms of z-scores, that should be the probability that z is less than 2, subtract the probability that z is less than 1. And we know how to find these probabilities in our table. So we pull up our table. We look for probability of z less than 2. That's here, 0.9772. 9772. And we're looking for the probability that z is less than 1. That's 0.8413. So those are exactly the numbers that I will use in my problem. Let's go back and take a look. So probability that z is less than 2, we found that that should be 0.9772. And probability z less than 1, 0.8413. I subtract the 2 and get 0.1359. So the probability that our sample mean IPO amount will fall between 120 million and 140 million is 0.1359. Answers my question. All right. And part C, lastly, it asks what is the probability that the sample mean IPO amount will be less than 95 million. Less than 95 million. So if I have a look at my distribution, and I know that mu x bar is here in the center, it's 100. Well, 95 is less than 100. So I'm going to put it over here on the left somewhere, 95. And what I'm really trying to find is the probability that x bar is less than 95 million. That should give me this area here to the left. So I need to find a z-score for 95 million. Same process, z sub 95 is equal to, I use 95 for x bar, then I subtract mu x bar, the mean of the sampling distribution, and I divide by sigma x bar, the standard deviation of the sampling distribution. So I get minus 5 over 20, or minus 0.25. That tells me that the probability that x bar is less than 95 is equal to the probability that z is less than negative 0.25, and I can find that in my table. So come to my table, open it up, and I'm looking for z less than negative 0.25, scroll up. Here's the negative 0.2, and this one here in the center should be negative 0.25. So I'm going to use 0.403 in my question. And get my answer done. All right, what next? Let's see. Okay, there's a part D for this question. Calculate the 99.5th percentile of sample mean IPO amounts. So let me just go back and write down mu x bar is 100, sigma x bar is 20. So I'm going to put that here. Help me remember. Still working on the same problem. I have mu x bar equal to 100, sigma x bar equal to 20. Now I'm asked to calculate the 99.5th percentile of sample mean IPO amounts. But I need to convert that percent to a decimal. And I think we know by now that to convert a percent to a decimal, we just divide by 100. In this case, I'm going to end up with 0.995, just divided by 100. So the question is saying, I need to find the z-score that goes with 0.995 probability, and then I want to translate that into the x value, the x bar value, which is the mean IPO amount. So let's look in our table and see what corresponds to 0.995. That's a really big probability, so I'm going to scroll down, 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 down. Okay, and here in the row that's 2.5, I see that I don't quite get 0.995 like I want, but I'm in between 0.9949 and 0.9951. And we know that in that situation, we just take the average. So this is 2.57, the z-score, and this is 2.58. So we'll just take the average of those two. Let's go back to our problem. Okay, so we have that z is equal to the average of 2.57 and 2.58. So I add them up and divide by 2, and I find 2.575. That's my z. And I want to use this information to translate that in terms of the sample mean IPO amounts. So then x bar, it's the same process we did with the normal distribution lecture. We're going to take this z-score, 2.575, and I'm going to remind you that 2.575 z-score means that I'm 2.575 standard deviations larger than the mean. larger than the mean of the sampling distribution in this case. So x bar is going to be 2.575 times the standard deviation of the sampling distribution. Then I'm going to add the mean of the sampling distribution. So 2.575 times 20, I get 51.5 plus 100. So that's $151.5 million. So if my IPO is $151.5 million, the fact that it's 95th percentile, that tells me that this is larger than 99.5% of initial public offerings. All right. Part E, compute the 0.5th percentile. So again, I want to do 0.5 and divide by 100, and that gives me 0.005. Okay, so I need to go to my z-table. I need to find the z-score corresponding to the probability 0.005. Scroll way, way, way up. And somewhere in here, we're going to find, well, I don't have exactly 0.005, but I'm between these two, so I can take their average. This is minus 2.57, and this is minus 2.58. So I'm going to take the average of those two z-scores, and I'm going to call that my z-score. So z is equal to the average of minus 2.57 and minus 2.58. Add them up, divide by 2, and I find minus 2.575 to be my z-score. And then I repeat the same process as above. So then x bar is minus 2.575 times 20, the standard deviation of the sampling distribution, and plus the mean of the sampling distribution, 100. So I get minus 51.5 plus 100, and that is 48.5. And again, I'm going to say $1 million. So if my initial public offering is valued at $48.5 million, then it is, because it's 0.5th percentile, this is larger than 0.5% of initial public offerings. But does anyone think that in Part E I did a little bit too much work? I could have saved some time somehow? Well, I think so, because Part E is closely related to Part D. So what I should have done, well, first of all, way back in Part D, I should have drawn my normal curve, because we should always draw our normal curve. We should throw right down here in the middle, our mu x bar is 100. We're talking about 99.5th percentile, so we know we're somewhere way up here. This is 99.5th percentile. So if this blue area is 99.5%, then the red area is 0.5%. Okay, well, I know that this graph is symmetric. That means that here in Part E, when I'm talking about 0.005%, we're or the 0.5th percentile. This red area here is 0.005. So it's exactly the same as my picture for part D, but flipped around, which means that I'm going to find the same z-score for both parts, but with two different signs, one positive, one negative. And that's exactly what I found by doing it from the table. So rather than looking at the table, if I had recognized from the beginning this symmetry, then I could have just said my z-score is going to be minus 2.575. I already know that because I found it in part D. If we didn't recognize that, that's fine. We have this method of using the table. We used it. We got the right answer. No harm, no foul. So then part F, what are the two symmetric values of x bar that contain the middle 99% of sample means? So let's see. 99%, let's convert it to a decimal. It's 0.99. I'm thinking about my normal distribution, which looks like a bell curve, and I'm looking for two values that are symmetric, so one on the left, one on the right, so that in between the two lies 99% of the distribution. So that means out here on the far corners is what's left over. We know that the total is 1, so I'm going to say 1 minus 0.99, which is just 0.01. That's how much is left over. But I need what's left over split into two pieces, one on the left, one on the right. So divide by 2, divide by 2, and I get that this is 0.005. So this red area is 0.005. This red area is 0.005. Then the green area in the middle is 99% of our data. Well, if we go back and refer to D and E, we already know how to find when 0.005 is on the right-hand side and when 0.005 is on the left-hand side. So I have the z-scores already that I need, and I know that they are 2.575 and minus 2.575 respectively. And I know that the corresponding values are $48.5 million and $151.5 million, because those were the answers in parts D and E. So I've answered the question. The two symmetric values of x bar that contain the middle 99% are $48.5 million and $151.5 million. All right, let's see what else. Okay, so we have one other topic for this lecture. So far we talked about sampling distributions. We talk a little bit about sample proportion. And we should have two new learning objectives to describe the sampling distribution of a sample proportion and compute the probabilities of sample proportion. And it's going to be fairly similar to what we just did. We are still talking about sampling distribution, but now instead of the mean x bar, we're talking about a proportion, which we denote p hat. That's here, p with the little hat on top, and we call that p hat. So the lecture note says, suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. So we have like a yes or no question, you either do or you don't. We can split the population into those two groups, the groups that do, the groups that don't. Kind of like our binomial distribution before. So from that type of a population, we're going to take a random sample of size n. So the proportion P hat is X, the number of individuals in the sample with the specified characteristic, divided by N, the size of the sample. This sample proportion P hat is a statistic that estimates the population proportion P. So from a sample, we can estimate the population. Okay. We have some more information here about the sampling distribution of P hat. For a simple random sample of size n, the shape of the sampling distribution of P hat is approximately normal, provided n times P times 1 minus P is greater than or equal to 10. And the mean of the sampling distribution P hat, mu sub P hat, is just going to be P. So this is kind of like where in the last type of sampling distribution, we said that mu x bar was just equal to mu. So now here we have mu P hat is just equal to the proportion P, whereas the standard deviation of the sampling distribution, sigma P hat, will be equal to square root of P times 1 minus P all over N. That's all inside the square root. Okay, so I know that's a bit much. Let's work through an example and you'll see what I mean. The example concerns credit cards, people who own credit cards or people who don't. So according to creditcard.com, 29% of adults do not own a credit card. So right away I'm thinking 29% should mean something. Then it says, suppose a random sample of 500 adults is asked, do you own a credit card? Describe the sampling distribution of P hat, the proportion of adults who own a credit card. So I'm going to say, according to creditcard.com, P is 29%, but I need to convert 29% to a decimal, so I divide by 100, and I say that's 0.29. And I have here that N is 500, because that's the size of the random sample of adults. So then we'll describe the sampling distribution. In order to do that, we need to find mu sub P hat. So mu sub P hat, from above we're told that's just going to equal P. So that's just going to be 0.29 for our sampling distribution. Sigma sum P hat should be the square root of P times 1 minus P over N. So in our case, square root of 0.29 times 1 minus 0.29 over N. And that happens to be square root of 0.29 times 0.81 all over N. And it's 500. So I can go ahead and plug that in. 500, 500. And I'll probably need a calculator to help me out. So I'm just going to pull up any online calculator. You probably have a desktop calculator or a calculator in your phone or any type of calculator that you trust. You can use it. So for our problem, we're going to take the square root of, I'm going to start some parentheses. So I need 0.29, and I need 0.29 times 0.81. And all of that I'm going to divide by 500. Take the square root of that. And I think maybe I made a typing error. Let's try it again. 0.29 times 0.81. Let's try it this way. We divide by 500 and then take a square root. All right, so 0.02167, etc. And we know that we're going to stop at the 4th decimal place. So we go to the 5th decimal place, we see it's a 7. 7 is larger than 5. So we conclude 0.0217 should be our sample mean. We add to it. So here we have 0.0217. Okay, I apologize, y'all. A little bit of technical difficulty there. But while I was working that out, I was able to notice that I made a mistake here. Hopefully some of you noticed as well. This should be the square root of 0.29 times 0.71. Because 1 minus 0.29 is 0.71. Previously I had written 0.81. Let's see, I think that should give us a slightly different sampling distribution standard deviation. So let's see, 0.29 times 0.71 divided by 500, and the square root of that is 0.02029, etc. So we're going to do the same thing. We're going to chop it off at 4 decimal places, which means I go to my 5th decimal place. It's a 9. 9 is greater than 5, so I round up, and it's 0.0203. So let's go back to our thing here. So standard deviation of the sampling distribution of the proportion is approximately 0.0203. So that's what we want to use for the rest of our problem. And we know that because we have sample proportion, we need to check if n times p times 1 minus p is greater than or equal to 10, then we can say that the shape is approximately normal. That's here. So let's check. N times p times 1 minus p, in this case, is 500 times 0.29 times 0.71. And we can plug that also into our calculator. .29 times 0.71 times 500. We have 102.95. So here, this is 102, and that's plenty large enough, larger than 10. So to answer our question, what would we say? How would we describe the sampling distribution? We would say the sample proportion follows an approximately normal distribution. And we know the mean of the sampling distribution, and we know the standard deviation of the sampling distribution. So with mu p hat equal to 0.29 and sigma p hat equal to 0.0203, and that would answer that question. But we have more questions. Let's see. What is the probability that in a random sample of 500 adults, more than 30% do not own a credit card? So let's think about this. 30%. Well, first of all, 30% in terms of decimals, I can call that 0.3. Want to think about my normal curve. And I know right in the center should be mu p hat. the mean of the sampling distribution of the proportion, and that's 0.29. So if 30% is 0.3, well, that's a little bit bigger than 0.29. Okay, and I want to find out the probability that more than 30%, so that should be this area to the right of 0.3. What is that area? So, as usual, we need a z-score, and we'll find the z-score exactly the same way as in the other problems. Z sub 0.3, except now I'm going to say this is p hat, 0.3, and I subtract mu sub p hat, the mean of the sampling distribution of the proportion, 0.29, and then I divide by the standard deviation of the sampling distribution of the proportion, and that's 0.0203. We'll definitely use the calculator to help us. So 0.29 minus 0.3, rather that's 0.3 minus 0.29, and that's clearly 0.01. Then we need to divide that by 0.0203, and we find 0.4926 and so on. But since we're talking about a z-score, and we know that our z-table, we only have z-scores going to 2 decimal places, so we're going to chop it off round here. So look at the third decimal place, it's a 2, it's smaller than 5, so we don't add anything, we just stop at 0.49. So I'm going to call my z-score 0.49. Okay, and then it's asking me for the probability, so we go to the table, we look at 0.49. And that should be scrolled down, positive 0.4, all the way to the end, 0.6879. So we're going to say the probability that p hat is less than, pardon me, more than 0.3. And that's equal to the probability that z is larger than 0.49. But we know that that's the probability, that's 1 minus the probability that z is less than 0.49. And that's what we just found in the table. So it's 1 minus 0.6879. .6879. So we get 0.3121. And that is the probability that in a random sample of 500 adults, more than 30% don't own a credit card. Now, what is the probability that in a random sample of 500 adults, between 25 and 30% do not own a credit card? So let's examine the situation. Take a look at our curve. We know that right in the middle is mu sub p hat, the mean of the sampling distribution of the proportion p hat, which is 0.29. And the problem has asked us about the values 30%, which we know we can convert to a decimal and call that 0.3. And 25%, if we convert to a decimal, is 0.25. So one is smaller than the mean of the sampling distribution, one is larger than the mean of the sampling distribution, and we're looking for how much is this area in between. Well, we've done problems like that before. So we know that I'm going to take the area of what's less than 0.3 and subtract the area of what's less than 0.25. So how do we write that? We say the probability that 0.25 is less than p hat is less than 0.3. And then we need to find the z-scores. because we'll say that that's equal to the probability of p hat less than 0.3, subtract the probability of p hat less than 0.25, and I'm going to convert those to z-scores. All right. So z sub 0.3, I already know, I have it up here. But let's find z sub 0.25. Same process. I take my p hat from the problem, and I subtract the mean of the sampling distribution of p hat, that's 0.29, and I divide by the standard deviation of the sampling distribution of p hat, and that is 0.0203. Probably need my calculator again. So 0.25 minus 0.29 divided by 0.0203 gives me minus 1.97044, etc. But again, this is a z-score, so I'm just going to keep that minus 1.97. Use that as my z-score. Minus 1.97. And then the next decimal place was a 0, so I didn't have to round up. Just keep minus 1.97. I already know that z sub 0.3 is equal to 0.49. So then I can say, I can translate this over here on the right to be the probability that z is less than 0.49 minus the probability that z is less than minus 1.97. And those are values that I can find directly from my table. So let's do that. Probability of z less than 0.49. Well, that should be 0.6879, same as in the previous part of the problem. And the probability that z is less than negative 1.97. I will scroll down to the column, the row that has negative 1.9, go over to the column that has 0.07 at the top, and I find that should be 0.0244. So I'm going to take the difference of those two numbers. So here I have 0.6879. Subtract the number that we just found in our table, 0.0244, and I get 0.6635. Which answers my question. The probability that in a random sample of 500 adults, between 25% and 30% don't own a credit card is 66.35%, or 0.6635. All right. So our last question here, would it be unusual for a random sample of 500 adults to result in 125 or fewer who do not own a credit card? So we got a couple things going on here. But the first thing that I noticed is they're telling me the number of adults, 125 or fewer, but all of the other problems so far in this section gave me percentages, 30%, 25%, 30%. So how do I convert 125 adults into some percent? That's where we go back to, at the beginning here, p hat is equal to x over n. So it's simply x is 125, n is 500. It's 125 out of 500. So that's the first thing. We're going to say p hat is going to be x over n. So x is 125, n is 500, and that should be 1/4, or in a nice decimal form, 0.25. And that reminds me, I think I already know something about 0.25 from the previous problem. So now maybe I can answer this question. Would it be unusual to have this, and why? Well, so we need to know what it means to be unusual. And in our lecture on normal distribution, I misspoke just a little bit, so I'm glad I have a chance here to clear this up. So I said in that video that being unusual and being an outlier were the same. So I'm going to clear this up here. More than 3 standard deviations above or below the mean, we call that an outlier. And outliers are highly unusual. But if we are between 2 and 3 standard deviations above or below the mean, then we are moderately unusual. So here in my problem, I'm going to go back to the previous part, and I found out that for 0.25, my z-score was negative 1.97. And I know that the z-score tells me how many standard deviations away from the mean I am. So if I have a z-score of negative 1.97, then I'm almost 2 standard deviations, but less than 2 from the mean. So in this case, that is actually not falling into this category of more than 3 and not falling into this category of between 2 and 3. So it is actually not unusual. It's kind of cutting it close, but it's not unusual. So we would say, since the z-score is greater than negative 2, the data is not unusual. And that would be how we would answer that question. So I apologize for any confusion. Being an outlier and being moderately unusual are kind of 2 different categories. And so technically, if we have a standard deviation, if we have a data point that's more than 3 standard deviations from the mean, then we definitely say it's unusual. But even if we're between 2 and 3, we would still say moderately unusual, and that's the mistake I made last time. In this case, we're less than 2 standard deviations from the mean, so we are usual. Okay, I think that's the last question on this lecture note. So hopefully you have met your learning objectives. If you go back and ask yourself, can I explain the sampling distribution, describe the sampling distribution when the population is normal, find the probabilities in percentiles? Can I describe the sampling distribution of the sample proportion and compute those probabilities? Then you should have met your learning objectives. Otherwise, do feel free to give Dr. Doss a quick email and he'll be happy to answer your questions.